Can we protect the planet by crashing a spaceship into an asteroid to prevent a catastrophic collision? DART could have the solution. Robots used by NASA for deep space exploration are often technical marvels made to last. At the edge of the solar system, the Voyager probes have been faithfully running for decades. With its impressive heat shield, the Parker Solar Probe spins around the Sun, where it will hopefully remain for many years. Although it has encountered various difficulties, Lucy is currently on a mission to visit a few space rocks close to Jupiter. The mission is expected to last for the next 12 years. It wasn't intended for DART, Double Asteroid Redirection Test, to advance solar system research for decades. The spacecraft was first launched in November 2021, and on it simply smashed into an asteroid. It is now completely ruined, yet its demise was always meant to be. DART is NASA's trial run of a planetary defense system designed to slam spacecraft into approaching asteroids to steer them away from Earth. Before there is a real need, NASA and other organizations want to conduct a vital test, an on-orbit demonstration of asteroid deflection. In order to change an asteroid's speed and trajectory, NASA is demonstrating kinetic impactor technology with the DART mission. DART will be the first space mission to ever show how an impactor can deflect an asteroid. From the Californian Vandenberg Space Force Base, the spacecraft was launched on a SpaceX Falcon 9 rocket. More frequently than you may imagine, asteroids, which range in size from refrigerators to automobiles, hit our planet. Thankfully, much of the rock in these impacts burns up in the Earth's atmosphere, making them generally not too dangerous. However, as you may recall, a huge space asteroid known as Chicxulub killed off dinosaurs roughly 66 million years ago. The DART mission's goal was straightforward. NASA wanted to know if humanity could collide with an asteroid without wiping out humans. As a proof of concept, the spacecraft then collided with the small asteroid Dimorphos, which is orbiting Didymos, a larger asteroid. When Dimorphos was roughly 7 million miles from Earth, the DART spacecraft autonomously steered toward it and collided with it at its closest point to our blue planet. The DART team thought that the target asteroid's course and speed would be modestly altered upon impact because it is around the same size as the Washington Monument. The lesson here is that this is essentially a technology demonstration, a technique for NASA to get important knowledge on how we can one day divert a terrifying asteroid that is actually headed for Earth. To be clear, our planet was never in danger from this specific drifting rock. However, if DART was effective in diverting Dimorphos somewhat from its track, we will know we might have a viable strategy for one day evading potentially hazardous asteroids. It was created to evaluate if a spacecraft impact could cause an asteroid to be deflected due to a change in momentum. There is no real risk to Earth from the asteroid chosen for the test. The mission was launched from Earth in November 2021, and on September 26, 2022, it purposefully collided with Dimorphos, the asteroid Didymos minor planet moon. Initially, the European Space Agency, ESA, and NASA had separate plans for missions to test asteroid deflection techniques. However, by 2015, they had formed a partnership called IDA, Asteroid Impact and Deflection Assessment, involving the launch of two independent spacecraft that complement one another. The proposal called for the launch of the European spacecraft AIM in December 2020 and DART in July 2021. In order to learn more about the composition of the larger asteroid and its moon, AIM would have orbited it. On September 26, 2022, DART would then kinetically strike the asteroid's moon during a near encounter to Earth. This approach of asteroid impact avoidance has already been used by the Impactor spacecraft of NASA's Deep Impact Space Probe, which weighs 372 kilograms, 820 pounds, to analyze the structure and content of a comet. It unleashed 19 gigajoules of energy upon impact, the equivalent of 4.8 tons of TNT. Created a crater up to 150 meters, 490 feet, wide, lowered Comet Tempel 1's perihelion by 33 feet, altered its orbit by 10 centimeters, 3.9 inches, and predicted a change in velocity of 0.0001 millimeters per second, inches per second, after impacting the comet on July 4, 2005, at a speed of about 10.2 kilometers per hour, miles per hour. Acquired target, Dimorphos. Didymos, a half-mile wide gray space rock traveling through our solar system, gently gravitationally leashes a partner asteroid with its gravitational tug. Dimorphos, the second, smaller component orbiting Didymos, was the object of DART. Dimorphos was chosen for the test by the DART scientists because of its orbit around Didymos, which resembles that of potentially dangerous near-Earth asteroids orbiting the Sun. Asteroids could collide with Earth because they are gravitationally tied to our star. However, Dimorphos' orbit is tied to Didymos rather than to the Earth or the Sun. This makes it the ideal testing environment for NASA, who attempted to crash DART onto the little rock in order to observe how this might affect the orbit of its larger companion. The strength of the crash, according to NASA, would be sufficient to change Dimorphos' orbital period by a few minutes. Calculations indicate that the impact will move Dimorphos closer to Didymos. The government will start poring over data from the spacecraft's trajectory and last seconds, as well as from Dimorphos' revised path after impact, to determine whether those projections were accurate. Generally speaking, our goal is to slow down the incoming object by around a centimeter every second. Although that's not very quick, if you do it far enough in advance, you can make it completely miss the Earth, according to the mission summary provided by the Applied Physics Laboratory at Johns Hopkins University. Deflection by kinetic impactor is one of many strategies proposed to protect humanity from asteroids. The approach was used intergalactically for the first time, according to the team. According to NASA's Planetary Defense Chief Lindley Johnson, this strategy is regarded to be the most technologically advanced approach for mitigating a potentially harmful asteroid. It will aid in the improvement of asteroid kinetic impactor computer models and provide information on future deflection strategies for potentially hazardous near-Earth objects, according to planetary defense specialists. Imagine your friend is riding a skateboard really quickly and is approaching your dog. You might run across your skating friend as one chaotic means of rescuing your dog. The energy you've built up changes your friend's direction and slows them down when you collide with them. You've just developed into a kinetic impactor that can knock your skating friend off balance and save your puppy. DART is anticipated to function similarly, but it doesn't seek to defend any canines. Rather, it seeks to divert the skateboarder's attention. The school bus-sized spacecraft collided with Dimorphos at a speed of around 4.1 miles per second. 14,760 miles per hour is about that speed, 23,760 kilometers per hour. According to NASA, the small asteroid's orbital speed should alter somewhat upon impact, resulting in an orbital period that is several minutes shorter. Dimorphos is not a threat to Earth, but Earth-based telescopes can easily document the bump's effects because the hit occurred at a distance of just around 7 million miles, making it possible for observers to track changes in the rock's orbit around its companion. As a result of these discoveries, scientists will be able to improve planetary defense tools using crucial data from the DART prototype. DART was fairly easy to use. It was a reasonably priced metal box with a single camera, 2 extendable roll-out solar panels for power, and a smaller satellite, or CubeSat, that was launched just before impact. The spaceship was destined to die on a suicide mission, thus having few tools made logical. The DART spacecraft has the following specifics. $308 million was spent. Weight, 1,210 pounds, 550 kilograms, at impact, 1,345 pounds, 610 kilograms, at launch. Size of the box, 3.9 by 4.3 by 4.3 feet, 1.2 by 1.3 by 1.3 meters. Dimensions of a solar array, each is 27.9 feet, 8.5 meters. 2 other instruments are a CubeSat and a Draco camera. engine, xenon thrusters, and ion propulsion technology. Although the payload of the Dark spacecraft was quite little, the team's programming for the course was very sophisticated. This is due to the courageous small craft's ability to behave on its own throughout the mission. DART until the end. Even though the spacecraft's tools were few, they were essential. Asteroid size, shape, and geologic makeup were all measured by the Didymos reconnaissance and asteroid camera for optical navigation, or DRACO, device's ultra-high-resolution camera. DART also had a metal oxide semiconductor and an image processor that enabled the spacecraft to pinpoint Dimorphos' precise location and transmit that information in real time to Earth through an antenna. This is all for today. Thank you for staying with us. Don't forget to like and subscribe our channel. See you soon.